କଣ ଆଣିଚଲ? ଏ ବାଳେଇ ଭାତ ହେଇନି କିଲୋ ଘରେ? ଖାଇନ କି ତମେ? ଖାଇନ? ଆଉ କଣ ଖାଇଛ?
Okay, good evening, everyone.
Good evening, ma'am.
Good evening. So today is our third class. Stereochemistry part we have completed in the uh, previous week. So this week we have reactive intermediates. Actually, as you have asked about the questions, previous year questions, I checked the IGNOU site. Only 2024 December question is available. You can just go there and check the downloads. And in the downloads, you can see the actually uh, questions. You just try to download all the questions. If you can, then I will try it tomorrow or somehow. Okay.
Okay, thank you, ma'am.
Yeah, you just check there. I got the questions only for 1 year. Means the previous year questions are there. I was not able to see the um, year before last year. So only last year questions you can just check, and I think the questions are very good. Means not very tough questions were asked last year. So I hope you all can just go through it. Okay, so now I will start my today's presentation. The slides are visible, my presentation slides.
Yes, ma'am. Yes, ma'am.
Okay. Okay, so today we will discuss about your reactive intermediates, and actually, we have like these six intermediates: carbocations, carbanions, free radicals, carbons, nitrins, and arynes. So today we will discuss about our carbocations and carbanions. And before going in detail about these reactive intermediates, we should know that what are these intermediates, how they are formed. So to know that, we should know the reactions, reaction mechanisms. So there are some fundamental basic concepts in your organic reaction mechanisms. So first aspect is how the bond is broken or how the bond is formed. So we can know the mechanism by knowing that how the bonds are being formed or how the bonds are being broken. So there are actually two types of bond fission, with bond breaking or bond fission, that is known as bond fission or bond breaking. Lysis means breaking. So it can be bond heterolytic bond cleavage or homolytic bond cleavage. Hetero means like when in a bond we have two electrons in a bond. So when both the electrons go to one atom only, then that is your heterolytic bond cleavage, because there is not equal distribution of electrons. So that is a heterolytic bond cleavage. For example, when a bond between A and B, that gives you A plus B minus or A minus B plus. That means both the electrons that is present in the bond is either going to your B atom or it is going to your A atom. So that is your heterolytic bond cleavage. And in the case of your homolytic bond cleavage, both the electrons are equally being shared. Like you have two electrons, one electron will be taken by your A atom and one electron will be taken by your B atom. So that is a type of homolytic bond cleavage. There are some typical reactions. Some reactions are there where there is the involvement. Here we have just seen one bond is being broken, but there are some reactions you will see in pericyclic reaction, which is your 4n plus 2 Diels-Alder reaction, sigmatropic rearrangement reaction. Some reactions are there where there is the simultaneous movement of your electrons, or bond breaking and bond formation are taking place at the same time in a concerted manner, or rather that is known as a concerted manner. So those reactions, your pericyclic reaction, where actually you form a cyclic compound where your there is actually orbital overlap of your LUMO and HOMO takes place. Next is What are the types of arrows we mostly use in organic reaction mechanism? We just do a forward arrow, that is a general purpose that shows the action, that is a normal arrow. Next one is a equilibrium arrow. So this depicts a reversible process. That means the reaction is taking place both for in a forward direction as well as in a backward direction. Okay, in a reaction, actually organic reaction, we have a substrate, we have a reagent. So the product and we get a product. So reactant side giving rise to product, and sometimes product side can give rise to your reactant side. So that is a equilibrium arrow which depicts a reversible process. But somewhere you can just see like these arrows where this reversible, here we have of equal wavelength the reversible arrow, but in this case this is of unequal length. These arrows are of unequal length. So in this arrow depicts that the equilibrium strongly favors products, or the equilibrium lies more towards right or the forward direction. Reaction in the forward direction is more the reaction rate, and that is the opposite when the for this type of arrow. Then we have a resonance arrow which shows the interconversion between your resonating forms, between your mesomeric forms, where electron delocalize. We just show different structure of the same compound by electron delocalization. That is a resonance arrow, which is a double-headed arrow, this one. Next is the dashed reaction arrow. We can just say, okay, what are can be the steps, theoretical steps, that is a dashed reaction arrow. Next is most of the mechanisms we deal with these curve arrows, where we have a double-sided arrow, curve arrow, but a double-sided arrow. So that is shows the movement of an electron pair. So it will be always from the electron source to electron, like where it is going. Next is a curved arrow, but here this is known as also fish hook arrow. Fish hook arrow. This shows the movement of a single electron. This looks like a fish hook. So that is also we depict mechanism through this. Then sometimes you can not very often we see these arrows. This is a broken arrow which shows an unsuccessful reactions, and retrosynthetic arrow. That means we can get this product starting with the starting materials like this. So this is a retrosynthetic arrow. I think you will learn this in your next semester maybe. Retrosynthesis is a actually is a vast area also in organic chemistry, because we know that we have this product, how what would be our starting materials. We can do it by this retrosynthesis method. Next is we have some reagents. Actually in organic chemistry we have a substrate where our reaction is going to take part in that reactant, and we have some reagents, and among those reagents we have nucleophiles, electrophiles, and some free radicals. I have listed here some nucleophiles and electrophiles. Nucleophiles are actually your electron-rich species capable of donating a pair of electrons to one electron-poor species. Nucleophile, that means it is your nucleus-loving. Okay, so nucleus loving means we will love the nucleus, mostly our electron rich species. So it can be either a negatively charged species like chloride, bromide, iodide, and it can be neutral where you have a lone pair of electron. For example, in water, we have two lone pair of electron on oxygen. So it is possible to donate this electron. Even in case of RLi, that is, although that seems neutral, but here we have a carbon lithium bond. So lithium is more electropositive as compared to carbon, or we can just say carbon, the electronegativity of carbon is 2.5 and the electronegativity of lithium is around 1, I think. So there is carbon is more electronegative as compared to lithium. So that is more, or what, negatively charged, delta minus. Here we have a delta plus. So nucleophiles are electron rich species which are capable of donating a pair of electrons, and your electrophiles, just the opposite, electron loving, would love the electrons. That would be your positively charged species, or neutral species having electron deficient center. Electron deficient center. So for example, dichlorocarbon, in case of your dichlorocarbon, we have on this carbon, we have 6 electrons, because carbon 2 and 2 bonds it have formed. So in total it has 6 electrons. So that its octet is not complete. So that is the electron deficient center. And in RCOCl, So this carbonyl carbon, it is attached to carbon oxygen double bond, and here we have another negative group. So this acquires a delta plus character. Although this is neutral, but it has a electron deficient center. Similarly, you can just see carbon dioxide also. We have a deficient center, electron deficient center at carbon. So these are electrophiles because they are electron deficient. And when we have a positively charged species, we do not have to say, but means it is obvious that these are electrophiles. And whatever reactions, most of the reaction, mostly our in organic chemistry, vast majority of reaction, most 90% of the reaction are the reactions between a nucleophile and an electrophile. So whenever you donate use your arrows, so nucleophile and electrophile, so this arrow shows the movement of your electrons. So nucleophile is the electron rich center, so that is the source, and it will go to electrophile, never the other way around. You do not say in that way. In your reaction mechanisms, always nucleophile to electrophile. Next is your hard, soft, acid, and bases. Actually, in nucleophiles, these are the donating a pair of electron. So electron donors, we can just say these are electron donors, nucleophiles. So that is also, nucleophiles are also your Lewis bases. Okay, so and electrophiles, we can say those are your Lewis acids. Not all we cannot define in terms of your Lewis acid and Lewis bases. Sometimes you may not have your electron pair to donate. So there is some other concept, that is your hard and soft acids and bases. And to understand the chemistry, organic chemistry, we should have a concept is hard and soft acids and bases, because somewhere you would see that on carbon your nucleophile is attacking, and somewhere it is attacking on other species, or somewhere you would see the electrophile is coming to your carbon, somewhere it is coming to your oxygen. So in that case, this sub theory, Pearson's sub theory gives very good concept. So what he did, that the acids and the bases, he just categorized it into hard and soft. So what are your hard acids, what are your soft acids? So hard acids have smaller ionic radii, and for example H plus, Li plus. So they have smaller ionic radii, high positive charge, and empty orbitals in their valence cells. They have empty orbitals in their valence cells. And soft acids are large because they have to have your empty orbitals to accommodate your electrons. And soft acids are large ionic radii, completely filled orbitals in their valence cells. It has low energy LUMO with a large magnitude of LUMO coefficients. Okay, what is LUMO? So HOMO and LUMO. HOMO corresponds to your highest occupied molecular orbital, and LUMO refers to your lowest unoccupied molecular orbital. Okay, so this HOMO and LUMO, they are your frontier orbitals. We say them frontier orbitals because they take part in your reaction, like our frontier soldiers. Whenever some enemy comes, frontier soldiers are there to first, they would be attacked by your frontier soldiers. Similarly, whenever our reaction occurs, these frontier orbitals actually react. So frontier orbitals are your HOMO and LUMO, that is your valenced orbitals. Actually in molecular orbital, we no longer have your atomic orbitals. Atomic orbitals combine to give molecular orbitals. So we have a HOMO and we have a LUMO. HOMO means highest occupied molecular orbital, and LUMO means lowest unoccupied molecular orbital. So in case of nucleophile, we see the energy of your HOMO, and in case of your electrophile, we see the energy of your LUMO. Because HOMO means nucleophile, you have the electron pair, so this electron pair of your nucleophile is going to attack, and LUMO, where your electron is going to reside, so it should have a LUMO. So uh, in case of soft acids, we have a low energy LUMO, and with a large magnitude of LUMO coefficients. And similarly, in case of your hard bases, they should be also small radii and highly solvated, mostly electronegative atomic centers. And soft bases, they are large atoms with intermediate electronegativity. And the correlating principle is that hard prefers hard and soft prefers soft. we will deal with some examples. So actually, the reason is soft, and the LUMO of soft matches the HOMO of your hard. Means a soft acid LUMO matches the uh, HOMO of your hard base, your soft base, and LUMO of hard acid matches the HOMO of your hard base. So some common reactions in organic chemistry, some are actually your substitution reaction when one group is being substituted by another group. Again, it can be of three types: nucleophilic, electrophilic, free radical substitution reactions. Similarly, addition reactions and addition reactions. In addition reactions, two molecules are added to give you one single molecule. Elimination reaction is just the opposite of your elimination addition reaction. From one molecules, we are getting two products. And rearrangement reactions, when you just see that some groups have changed its position. For example, this methyl group in the product, you can just see the methyl group has been migrated to another carbon. So that is a kind of rearrangement reaction. The groups are rearranged in the final product, their position has been different. And some polymerization reaction which give rise to a polymer. Okay. That hard and soft acid and base concept, what is the role of hard and soft basic acid base concept? So as you just see this alpha beta unsaturated carbonyl compound, we have, if I just do the, it is its resonating structures. We have two resonating structures in which we have a okay. Yeah, I can just okay. So here, if I just do this one, then we have a positive center here. And in the next exam, regenerating structure, this can be stabilized by conjugation or delocalization. So to give a positive charge here. So we have at two carbons, carbon number 2, we have a positive charge, and at carbon number 4, we have a positive charge. And the positive charge on carbon number 2 is actually more as compared to the positive charge on carbon number 4. So we can just say this is a higher charge, so this is a hard electrophile, and carbon number 4 is a soft electrophilic center. So whenever we use a strong electrophile or a hard nucleophile, hard goes to hard nucleophile will go to hard center, and soft nucleophile will go to your soft center. So we are using two organometallic compound here. One is your grignard here, and another is your organocopper. So among organomagnesium and organocopper, magnesium and among magnesium and copper, the electronegativity difference, if you just see, magnesium is more electronegative, more electropositive as compared to copper, electropositive. I'm just saying here electropositive character. That means the carbon magnesium bond is more ionic. More ionic. Okay, because magnesium is more electropositive as compared to your copper. So here the negative charge, and here the negative charge on carbon. Here the negative charge on carbon is more. So this is hard. And here the negative charge on carbon is less because copper is less electropositive. So the electronegativity difference between carbon and copper is very less. So carbon bearing negative charge is less. So this is a soft. So now this hard carbon, or this is my nucleophile. So this is hard nucleophile, this is your soft nucleophile. So hard nucleophile will go to your hard carbon, hard electrophilic site, and your soft nucleophile will go to your soft electrophilic site, giving rise to two different products. So this is the alkylation occurs at carbon number 2, and this is the alkylation that occurs at carbon number 4. So first, then we consider, like in organic chemistry, whatever reactions, whether organic or inorganic, everywhere we have to consider the thermodynamics as well as your kinetic aspect of the reaction. Thermodynamics just says whether the reaction is feasible or not, whether that would be spontaneous at this temperature or not. So thermodynamics deals with that, and kinetics deals with like how fast the reaction is going to occur. What is the speed of the reaction that will be done by your kinetics. So in case of thermodynamics, one is your very important point, that is your change in free energy. Del G zero is known as your standard free energy change. So this is the if it is negative, when del G zero is negative, that means the reaction is spontaneous. The reaction will occur, or that would go in a forward direction. And here R is your gas constant, T is your temperature in Kelvin, and this capital K is your equilibrium constant. So this equilibrium constant, suppose for a simple reaction, A moles of A plus this is B moles of B, giving rise to C moles of C plus D moles of D. So the equilibrium constant is given as concentration of C, that is concentration of products divided by concentration of your reactants raised to the power of their coefficients. So concentration of C raised to the power C, concentration of B. Sorry, any doubt? Okay, kindly mute your phone or whatever device you are using. Sagarika jelly. Okay. So, like, okay, in a reaction, suppose we have a reaction where A moles of A plus B moles of B giving rise to C moles of C and D moles of D. So the equilibrium constant K can be equal to concentration of C, that is your power of your product concentration, product of your concentration of your products divided by concentration of your reactants. So and it depends. K would be more when your product concentration would be more, or that would be in your forward direction. So in a so for a negative value, that means del G zero would be, if del G zero is negative. Okay, if the del G zero would be negative, so mostly our spontaneous reactions, del G zero should be less than zero, or it should be negative. So for a small, very small change in, if you just see, for a very small change in del G, that makes a big difference in your K value. K equilibrium value. But just see, for 0, the K equilibrium is 1.0. Percentage of more stable state at equilibrium is 50. But if you just change it to 10, your K equilibrium value is 57. So that is a very drastic change. Of a small change in del G would give you a big difference. So what does del G zero tells about? If del G zero for a reaction is negative, the product will be favored at equilibrium, and if del G zero for a reaction is positive, the reactant will be favored at equilibrium. And if del G zero for a reaction is 0, the equilibrium constant for the reaction will be 1. That means the rate of forward direction is equal to the rate of your backward direction. Next is some other factors on which your del G zero value depends. Now that is del G zero, that is change in our Gibbs free energy, standard free energy change, is equal to del H zero minus T del S zero. So del H zero is your enthalpy change. Enthalpy is a measure of the total energy of a system at constant pressure. And entropy is a measure of the disorder or randomness of the system's molecules. So it quantifies how much of a system's energy is unavailable for useful work. So enthalpy change, that is your enthalpy of your products minus enthalpy of reactants. Similarly, entropy change is equal to entropy of your products minus entropy of your reactants. So the del G zero value depends on change in enthalpy minus T del S zero. So just in del G0, I can just write the equation minus RT ln K is equal to del H0 minus T del S0. Or ln K is equal to minus del H0 divided by RT plus del S0 by R. So if the reaction is exothermic, when reaction is exothermic, del H0 is negative. That would be your negative. So then at higher temperature, the equilibrium constant will be smaller because when the reaction is exothermic, so the first term becomes your negative, so that would be del H0 by RT. So this is positive and we have del S0 by R. At high, for exothermic reaction, del H0 is negative, so del H, this becomes minus of minus, so that would be your plus del H0 by RT. So here, if we increase the temperature, because T is in your denominator, so if we increase the temperature, that is going to decrease your equilibrium constant. So the at higher temperature, equilibrium constant will be smaller. But for an endothermic reaction, your del H is positive. Endothermic means here heat is, we require heat, or we, so here del H is already positive. So for that, now for that our ln K would be equal to minus del H0 by RT plus del S0 by R. Okay, this term does not depend on your T, but this term minus del H0 by RT depends on your temperature. So for an endothermic reaction, if you increase the temperature, in that case, your K would increase because it is already negative and temperature T is in your denominator. So with increase in temperature, you have negative and again that would be negative. So that would increase the actually your equilibrium constant, or K value will increase. So for exothermic reactions, higher temperature, equilibrium constant will be smaller, and for an endothermic reaction, the with increase in temperature, K value increases. So for the thermodynamics, for the organic chemist, free energy change or del G0 in a reaction is proportional to ln K, and del G0 and K are made up of your enthalpy and entropy terms. Del Enthalpy change is the difference in stability of the reagents and products. Entropy change is the difference between the disorder of reagents and that of the products. The enthalpy term alone determines how K varies with temperature. Next is your kinetic consideration. So suppose kinetics mostly says about your rate of reaction, how fast the reaction goes. So rate of a reaction is actually the rate of change in concentration of your reactants reactants or products with respect to your time. For suppose for some infinitely small change dA at time dt, so that would be rate would be equal to minus dA by dt, that is the change in concentration of a with time. Okay, we have given minus here because this is your reactant, and with time its concentration decreases, the reactant concentration decreases, but in case of product we just give positive dc by dt. So that is the change in concentration of your reactants and product, or we can just say the change in actually the decrease of the concentration of the reactant or the formation of your products. And rate of a reaction is directly proportional to the concentration of your reactants, not here products. Here they depend on the concentration of your reactants, and K is a constant that is known as your rate constant. The other one was your equilibrium constant, and this is your rate constant. And whenever we have a many step reactions, among the many step reaction, mostly for a complex reaction, some reactions are slow as compared to the others. So the slowest step of this reaction actually determines your rate. So that's why that is known as your rate controlling or rate determining step, or rate determining step. For example, whenever you have a two-step process, okay, so okay, this is the highest point is known as your transition state, we will deal with it. But whenever we do a reaction like some bond breaking and some bond making goes on, so this is a two-step reaction, it takes part in two steps. So the first step, you just see in this case it takes up more energy, and in the second step it takes up less energy. So it takes up more energy means this is a slow step, and this is your first. because here you have to acquire more energy. That means it has to go very slowly. And in this one, the first step, it does not need more energy, and in the second step, you need more energy. So this is your slow step. So among these two, this one, this in this case, this is the slowest step. So we would say that the first step is your rate determining step, RDS, that is your rate determining step. And in case of the second, this one, step 2 is the rate determining step. So what is a transition state? Actually, whenever we do a reaction, some bonds are being broken and some bonds are being formed. For example, in this reaction, that is a nucleophilic substitution reaction, you just see the carbon iodine bond is being broken and carbon oxygen OH bond is being formed. So to go from the reactants to products, it has to undergo many energy changes. So here, actually, there would be a state where the bond breaking and bond formation is going on, and that is the maximum energy. That is the maximum energy through which the reaction is proceeding, and that state is known as your transition state. And it cannot be isolated because it is an energy maximum, and any change in its structure leads to a more stable arrangement. A transition state is often shown by putting it in square brackets with a double dagger superscript. Okay. And the rate of reaction, actually, whenever we say that, the rate of reaction depends on the energy of this transition state. The higher the energy barrier, okay, this one is the energy barrier. The higher the energy barrier, the lower would be the rate. If that means if it would be higher, then you have to need more energy. So the rate would be slower. If lower the energy, then you need less energy and the rate of reaction would be faster. So for example, in this reaction, in this addition reaction, nucleophilic addition to your carbon acid derivatives, so it first involves it involves two steps. In the first step, it involves the attack of the nucleophile to your carbonyl carbon to give a tetrahedral intermediate, and then your departure of the leaving group. So it has two steps, and in these two steps, we can here we have taken okay. And so, for example, in this case, the first step, your starting material is higher in energy and your product is in lower in energy. But to go from the starting materials to product, it goes through two steps. And in the first step, it is the slow step, and it gives you an intermediate, actually, that it stays here for some time and then it gives rise to your product. So transition state, this is your transition state, it is your intermediate. So transition state represents an energy maximum, and an intermediate on the other hand is a molecule, because transition state is not a molecule, but intermediate is a molecule or a species that represents a localized energy minimum. It stays here for some time, actually. So that is the your rate determining step. In the intermediate, it stays here sometime. Suppose you go from your uh, home to your office, and between we stay somewhere for some time, for 1 minute or 2 minutes, you take a break. So that is your intermediate step. Similarly, in your reactions, you from starting materials to going to the product, there some species or some molecules are being formed. So to form that molecules, it has to pass through also a transition state, and again from that molecular ion, which is your intermediate, to go from that to product, it has to pass through a transition state. So here we have two transition states, and intermediate is a molecular ion that represents a localized energy minima, and energy barrier must overcome before the intermediates forms. And next is your how we determine which product we would have, thermodynamic versus your kinetic control. Again, the same reaction, that is your 1,3-butadiene. So now we have when we add hydrochloric acid, HCl, hydrogen chloride, to 1,3-butadiene, so there is the possibility of two products. For example, 1,3-butadiene, first step is it would take out a proton. It will just add one proton, so that would give you a carbocation. Okay, the H would go here by your Markovnikov's rule. H plus would be taken out by here. H plus would be test. So you have two type of your and two type of intermediate is formed. Okay, so these are the resonating structures. So now the chloride can attack either this carbon or this can attack this carbon. So it depends on two parameters, which one is going to be more favorable, and it depends on the temperature. So one is known as your thermodynamic product, another one is your kinetic product. Why one is thermodynamic and one is your kinetic? In case of thermodynamic, more stable product is formed, more stable. Okay, so thermodynamics mostly deals with the stability, and kinetics mostly deals with your energy of your transition state or your activation energy, energy of transition state, or that is your activation energy barrier. So that depends mostly on your rate of reaction. So more is the high activation energy, lower would be the rate of the reaction. So among these two, we have now two kind of intermediates. So you just see this is our butadiene. It goes through one transition state, okay, to give you two intermediates, either this one or this one, to give rise to two products. So you just see the green one. Green one is going through a less energy transition state and giving rise to a product which is less stable, and the blue one is going through a higher energy transition state and giving rise to a more stable product. But when at a low temperature we would have more of this one because this is more stable as compared to this one, and so that would give rise to this product because the transition state, energy of transition state is less here. So that the primarily that is your kinetic driven product or kinetically controlled product. But whenever you have sufficient energy, then it can go to this intermediate and give rise to your thermodynamically stable product, that is your 1,4 addition product in this case, or thermodynamically controlled. So it depends mostly on your temperature and the energy of your transition state. Similarly, for this reaction, that is you can have in this alpha beta unsaturated ketone. Okay, so this is your alpha beta unsaturated ketone. So when hydrogen cyanide is attacked, it can undergo attack at the carbonyl carbon, direct addition at carbonyl carbon, or it can undergo conjugate addition. That means it can attack the beta carbon. It would end up addition at your beta product. So among these two, this one is your kinetic product and this one is your thermodynamic product, because this is more stable and this is your less stable. If we see the stability of your product, so just you see this is my starting material, and for this left hand side addition, directly addition to your carbonyl carbon, that passes through a less energy transition state, and it has this intermediate and giving rise to this product. But on the other hand, the other pathway shows a higher energy transition state, but in this case, the product formed is more stable. So it depends on if you have sufficient energy, you can give sufficient energy. In that case, even this kinetic product can again go back to your starting material and it can give rise to your more stable thermodynamic product. So it depends on your reaction conditions, whether it can be kinetically controlled or it can be your thermodynamically controlled. So, what are the points to note in your thermodynamics versus kinetic control? The thermodynamic product has a lower energy than the kinetic product. The highest transition state to the right is the higher than the highest to the left. Initially, the reaction will go to the left. In that case, if there is enough energy for the kinetic product to get back to the starting material, there will be enough energy for some thermodynamic product to form. The energy needed for the thermodynamic product to get back to starting material is very great. So once it is being formed, if you have more energy, then the kinetic products again come back to starting material and it can give you the thermodynamic product. But reverse is not true. If you are going to give more energy, then it cannot go back to your starting material and giving to kinetic product. The kinetic product is always formed reversibly. The thermodynamic product is formed irreversibly. At low temperature, direct addition is favored, but conjugate addition is favored at high temperatures. Next are some reactions. For example, to show this our common reaction, in which we can just show some one-step reaction, two-step reaction. The famous reaction is our nucleophilic substitution reaction. We have SN2 and SN1. In case of SN2, there is just concept the nucleophile attacks and the leaving group depart, and it takes place in a single step, single step, and it passes through a 5-center transition state. Okay, but same nucleophilic substitution reaction when we do with the tertiary tertiary alkyl halides, and in that case it takes place in two steps, where first step is the departure of your leaving group forming a carbocation intermediate, which we will deal with in the later part. Next, the nucleophile can attack your carbocation, so it goes through an intermediate. Okay, and it involves two transition state, and in this case it involves one transition state, and in this case we have a 5-center transition state, and in this case we have in the first transition state that is also 4-centered, and in the second transition state that is also 4-centered. In the first transition state where we have a departure of leaving group, and in the second transition state we have a attack of your nucleophile, and it passes through an energy minima that is known as your intermediate, that is your carbocation intermediate. So the rate of reaction depends on this carbocation intermediate. The lower is the energy of this carbocation intermediate, the more faster would be the rate of the reaction. Okay, so this involves your so you have a clear idea that what is an intermediate and what is a transition state, and the energy, actually this energy between your reactants energy and the energy of your transition energy, transition state energy, is known as your activation energy, because this transition state is also known as your activation state. Okay, next is how we know that the reaction is going through this pathway. So that is your study of your reaction mechanism. Mechanism means how the reaction goes in which pathway. So there are different methods. Non-kinetic, one is your non-kinetic method, in which one is your product identification. So you have to identify all the products formed, not only the major product but also your minor products, the simple products, means which you don't need. You think that okay, my major product is in this chlorination reaction of methane, my major product is formation of your chloromethane, but you ignore the formation of ethane, all those although it is 2%, it is formed in 2% or 4%. If you ignore these products, then you cannot identify the mechanism. So you have to identify all the products formed, not only your major product but also your minor products. Then only you can say okay, this may be the pathway or this may be the mechanism of this reaction. Next, you can also have evidence for an intermediate. If any evidence is being formed, then you can just have an evidence. For example, in the Huffman degradation, Huffman bromamide reaction, this is the intermediate you are forming. So if you can just have evidence, this can be actually quite isolated and it can be characterized. So from that you can just say okay, this might be the reaction mechanism or it is going through this pathway. Similarly, you can just sometimes some intermediates you cannot isolate. In that case, you have to arrest or quench the reaction or do the spectroscopic identification, or you can also trap your intermediates. How you trap your intermediate? For example, in this benzene intermediate, we will deal with tomorrow. We will discuss about benzene intermediate. So this benzene intermediate, like if you have anthracene in your mixture, you just add anthracene in your mixture, you get a product like this, so which can only give the evidence that benzene intermediate has been formed. And sometimes this product formed is also an evidence that your this is a 2+2 cycloaddition reaction, and in this case this is your 4+2 cycloaddition reaction. So this gives the evidence that this benzene intermediate is being formed. This benzene intermediate, you cannot isolate it, but you can trap it, that this is being formed. Okay, next is you can add a suspected intermediate. Suppose you think that it is going through this intermediate, so you add that intermediate if it is readily available, and you check if that is going to give the same reaction, give the same product under that specified conditions. For example, this bond richer rearrangement of beta nitronaphthalene, which gives naphthoic acid, first of all, they thought that okay, this might be the intermediate being formed. But under those reaction condition, it never gave your alpha naphthoic acid. That means hydrolysis of cyanide is not giving you COOH direct. It means it is not going through this cyanide is giving COH, but this is not going through this intermediate. So this rules out the formation of this intermediate. Next is some isotopic studies where some isotopes are studied to actually check the mechanism. For example, in this ester hydrolysis, uh, instead of normal water, where O16 normal water, they have taken the other isotope of oxygen, O18, and you can just check where that O18 is going where, because here all these oxygens are 16 16. So this observation led, like there are two possibilities. Like whenever we are doing hydrolysis, we can just break this bond, like the carbonyl after CO OC6H5. So we can just involve acyl oxygen fission or alkyl oxygen fission. This is your acyl group. After that oxygen, so it can involve this bond breaking, or this can involve this oxygen alkyl group bond breaking. So if this bond is broken, then this OH group, that is the oxygen where your um, isotope, the other isotope oxygen is there, that will end up attached to your carboxylic acid. If it is the other way around, then the OH group, that is 18 would end up in your alcohol. So it was actually seen that the O18, that is your isotopically leveled oxygen, is ended up with your carboxylic acid, not with your alcohol. So that means that the bond must be broken or has broken by your acyl oxygen bond fission, not alkyl oxygen bond fission. So next is isotope effect. Here you have used other reagent where you have leveled one, and here like you have to use a different isotope in the same your starting material. So any of the atom in your starting material, any one atom would be replaced by its isotope. So that is your isotopic substitution, and you have to check whether the rate, it depends on the rate of reaction or not. For example, if instead of hydrogen we check deuterium, because hydrogen, the bond, suppose it involves the breaking of the carbon hydrogen bond, so it would be difficult, the rate of reaction, if the rate of reaction depends on the breaking of carbon hydrogen or carbon, so if we replace hydrogen with deuterium, then it would have a effect on the rate of reaction, because carbon hydrogen bond is like if you just see the vibrational energy, so it would be more energy. It would give higher spectra or vibrational energy level at more, and carbon deuterium would give at less. Or it's if we just see carbon deuterium bond and 0 point energy is at lower position as compared to carbon hydrogen bond frequency. So it would be difficult to break a carbon deuterium bond as compared to carbon hydrogen bond. Or you can just see there would be relatively difference in your rate of reaction. So this kind, that is known as your kinetic isotope effect, because after your substituting with another isotope, it would be this rate of reaction would be altered. It may be more or less. So that's why that is known as your kinetic isotope effect. So this kinetic isotope effect is of two types. One is your primary kinetic isotope effect, and one is known as your secondary kinetic isotopic effect. So what is your primary kinetic isotopic effect? So for example, in this case, you just see this is an elimination reaction. In this case, if you just change the hydrogen here, okay, so this is an E2 elimination. So in case of E2 elimination, that takes place, the beta hydrogen is eliminated. The beta hydrogen is eliminated, and it is in a concerted manner. So that is a single step reaction. So if we just change this hydrogen with deuterium, you just see the rate of reaction for hydrogen and rate of reaction for deuterium, the ratio is 6.7. That means when hydrogen is there, the rate of reaction is 6.7 when we substitute it with deuterium. So this is a primary kinetic effect, so that you can just see that that gives a idea, like this is the reaction, actually the reaction mechanism like this. And suppose we just change this hydrogen, the same hydrogen, in case of your E1 elimination. In E1 elimination, the reaction is actually uh, takes place in two steps, in which the first step is the elimination of bromide, and then that is the slowest step, and the second step is your first step, is very fast. So in that case, the slowest step does not involve the breaking of your carbon hydrogen bond. So here you just see there would very less kh by kd, that is your relative rate of reaction is very small. That means there is almost equal. So in that case, we can say that the carbon hydrogen bond is not broken in your rate determining step. Another kinetic isotope effects also you can just see in SN2 reaction, where actually you do not have a carbon hydrogen bond breaking. So that does not depend on the rate of your reaction. Next is your, by doing some stereochemical studies also you can come to know the reaction mechanism. For example, in this SN1 reaction, where starting with your optically pure enantiomer, you are going to get a racemic mixture. That means both the enantiomers are being formed. So this can only be explained by that the first step, you the living group departs. There are some other evidence also, but this is a stereochemistry point of view. So that gives the evidence that first that means as you are getting two different enantiomers, that means the nucleophile must be attacking the carbon center from both the sides. So which is possible only that first the living group departs to give you a planar carbocation intermediate, and now the nucleophile can attack it from both the sides, from the same front side or from the back side. Front side giving rise to retention and back side giving rise to inversion. Retention means same as the configuration of your starting material. Inversion means it is the opposite of configuration of your starting material. So that gives rise to your racemic product. So this product the product, stereochemistry of the product determine the reaction mechanism. Similarly, in case of your SN2 reaction, if you start with S uh, plus enantiomer, or S, whatever be the optically pure enantiomer, and then it is giving you complete inversion in configuration. So it is, if it is 100% enantiomerically pure, this is also 100% enantiomerically pure. So this suggests that the nucleophile attacks from the backside. So this gives the evidence that there is nucleophilic attack and the departure of the living group taking place in a concerted manner. So that gives the evidence that means the so in that way you are getting your inversion in configuration of your product. Similarly, stereospecific and stereoselective reactions in the last class also we have discussed, like stereospecific. Suppose if we are taking transbutene, that is only giving you a product, meso product, but in case of your cis-2-butene, that is giving you a DL pair. Both the enantiomers are being formed. So that is from the product, from the stereochemistry of the starting material, and from the product you can determine the actually reaction mechanism. Then there is another effect that is known as your substituent effect, which is given by your Hammett equation. So don't get confused with the Curtin-Hammett principle, which we discussed in the last class. And this is a Hammett equation. So this Hammett equation, this relates the influence of meta or para substituent on the reactivity of a functional group in a benzene derivative. Suppose we have a benzene derivative X, and we are doing any kind of reaction. So if we have a substituent at ortho or meta, meta, para, or ortho position on the reactivity of your functional group in a benzene derivative. So if we have a group G at ortho or meta or para position. Okay, so this equation gives, it says that log K by K0 is equal to uh, rho and sigma. So where K and K0 are the constants for group when X is not equal to 0. So when, okay, he has given here X. So I am just putting this G, this one is your X. So when X is not equal to H, and at which position it is, and X is equal to H. Okay, so this is K0 when X is equal to H. That means you do not have any substituent, and K is your when you have any substituent. And sigma and rho are the constants for reaction conditions and substituents respectively. So rho is reaction constant and sigma is your substitution constant. So how these values are determined? Actually, they have taken into account the hydrolysis of your benzoic acid. Okay, in case of your benzoic acid is an acid, so that gives you benzoate ion. So it has a Ka value. Okay, Ka is acidity, ionization constant of your acid. So whenever we have a substituent in benzene, in carboxylic acids, we know that your electron withdrawing group, suppose we have at a para position, that increases the acidity, and if we have an electron donating group present at your para position, suppose I have put an electron donating group, CH3 group, that decreases the acidity. So what they did, like by substituting in this hydrolysis of your, like this is an not I can say this is hydrolysis, this is the ionization of benzoic acid. So in the ionization of benzoic acid, they studied the ionization constant. Okay, ionization constant for only benzoic acid, and by substituting X with different substituents. For example, meta or sorry, nitro, cyano, all these groups they have done. Okay, after doing that, what they did, like they plot log Ka by Ka0 with your different sigma values. Okay, they get a log K by K0, and you, when we do it, you get a sigma and you plot a graph. Okay, so that gives you a straight line with slope equal to 1. Here your slope is equal to 1. That is the value of your rho. Okay, so for benzoic acid, your reaction constant, it has been considered equal to 1. So when you plot for different log K by Kh, that gives you sigma, different sigma values for different substituents. So these substituents, you have different substituent values for different your okay, sigma values for different substituents. So then they have applied it in any other reactions of benzene derivatives. So this sigma values is of for your substituents, so which they get it from your benzoic acid, doing the ionization of your benzoic acid. So when they did the reaction, like for your phosphoric acid, benzene phosphoric acid, there they also did the log Ka by Ka0. Ka would be when X is equal to H, and Ka0 and Ka would be when X is equal to any substituent, and then plot it against the sigma value which they have obtained from your benzoic acid data, and they get there also they get a straight line, but in this case the slope is not equal to 0, not equal to 1, rather it has a other value like 0.76, and here slope is 2.54. So this gives the condition that log Ka by Ka0 is equal to rho and sorry, sigma and rho. So sigma is your substituent constant and rho is your reaction constant. So this constant is constant is actually applicable to one reaction. So this is a constant for one reaction only. So for this reaction, it has a rho value of 0.76 and this has a rho value of 2.54. So if you know the Ka by Ka0 value and sigma value, you have the data from benzoic acid, then you can find out your rho value by plotting a graph, and the slope gives the rho value. So what is its utility of this Hammett equation? So suppose we know the sigma and rho values for the various reactions and substituents, we can use this data to predict the equilibrium constant of the rate of reaction. For example, for the ionization of phenol, so suppose for the ionization of phenol, OH, H2O. So for the ionization of phenol, it has given for phenol the reaction constant is 2.26. For phenol only, the reaction constant is 2.26, and for paranitrophenol, the sigma value is 0.81. Okay. Uh, so in that case, you have to, if the Ka of phenol is known, okay, Ka value of phenol is known, then that of paranitrophenol can be calculated. So we know that log Ka by Ka0 is equal to sigma rho. So substituting, you just substitute all the values. You know the sigma values and you know the rho value. So you just take the antilog, that would give you Kp, that is the of nitrophenol, and of phenol is equal to this much. So from that you can find out the equilibrium constant of paranitrophenol. So similarly you can do, you can check many utilities of your Hermite's equation. So I hope we can take a break now, 5 minutes break. Hello, should we take a break now for 5 minutes?
Yes, ma'am.
Okay, we will resume at 7, 5 or 6. Okay, 5 minutes break we will take. So, okay, now we can resume. Hope all are back from the break. So, till now we have discussed about the different aspects of any reaction, like what is an intermediate, what is a transition stage, what is the mechanism, and what are the kinetics points, and what are the thermodynamics points. Next, there's this module actually have your reactive intermediates. So among them you have one intermediate, that is your carbocation intermediate. So in case of an carbocation, that means a cation that is a positive charge on a carbon. So how these carbocations are formed? So these carbocations are formed by the heterolytic bond cleavage of a carbon, and mostly in more electronegative element. So that is in this case, in heterolytic bond cleavage, as I have told, both the electrons are taken up by this more electronegative element. So this is mostly in case of a polar compound, where your carbon is less electronegative as compared to your the other atom. For example, when you have oxygen, mostly halogens, all those kind of things. So in that case, you generate one carbocation by the heterolytic bond cleavage. For example, in this tertiary butyl bromide, when bromine is departed, or when we break the carbon bromine bond, we generate a tertiary butyl carbocation and a bromide leaving group. And in some cases also, this carbon double bond can add up one H plus, one proton, so that you generate a carbocation. And similarly, whenever you have an alcohol or something, so that takes out one proton, and again this mm, departure of leaving group gives you one carbocation intermediate. Similarly, you have different type of reactions where carbocations are formed. For example, in this diazonium salt formation from primary amine, that gives you diazonium salt, and again this nitrogen is a very good leaving group, generating a carbocation and a nitrogen leaving group, because nitrogen is a very stable gas molecule, and that is a very good leaving group. So next is comes your structure and stability of your carbocation intermediate. So carbocation intermediate is actually carbon having three bonds and a positively charged basis. So in that case, carbon is sp2 hybridized, because carbon in the in your neutral carbon atom, you have four electrons in the valence shell, but in case of carbon plus, you have three electrons, and all the three electrons are taken off in bonding, because you have three bonds. So in total electron pair is 3, so that should be sp2 hybridized. So in that case, you have a pure p orbital which is vacant. So pure p orbital which is your vacant, because these sp2 hybrid orbitals are taken off in your sigma bond formation. So this carbocation, actually according to IPAC, it is known as your carbonium ion or a trivalent carbocation. And don't get confused, like to tell them as your carbonium ion, because ion means carbon having 5 bonds and a positive charge. Okay. So next is your carbocation stability. So to remember, carbocation is a positively charged species. So whenever you check the carbocation stability, we have it in mind that it is a positively charged species. So when it is a positively charged species, whoever is giving electron to it, or whatever group which is present near to it, should provide electron to it, then it will get more stabilized. So carbocation stability, there are many number of actually factors which affect the carbocation stability. One factor is your inductive effect. So here you just see, in case of your carbocation intermediate, it increases with the number of carbons attached to the carbocation increases. So methyl is less stable as compared to your primary, which is more stable as compared, which is less stable as compared to secondary, and which is again less stable as compared to tertiary. So among your aliphatic carbocations, tertiary is the most stable carbocation. Why these are more stable? Actually, these CH3 groups, the presence of these CH3 groups impart a positive plus I effect. So plus I effect means that is your inductive effect, or the groups which gives electron through inductive effect. So the more the number of plus I groups, that increases the stability of your carbocation intermediate. There is another effect that is known as your hyperconjugation. So what a hyperconjugation is, like whenever you have a carbocation intermediate, carbocation species, and next to it you have a carbon which has a hydrogen attached to it, then there would be orbital overlap between the p orbital, that is your p orbital of your carbocation, and the carbon hydrogen bond. So now this remains as if this you have a carbon carbon double bond, and this have a H plus. So this is a, like previously we have a, we would check it. So normally it is a conjugation where you have a pi bond towards the carbon, and here there is bond between your carbon carbon, whether that bond is going out, but still you have the bond there. So it is positive charge here. But in this case, in case of hyperconjugation, as you see, when this gets overlapped with this atomic orbital, so now there is no bond between carbon and hydrogen. So this is not actually resonance form, but still that gives more stability. So this is your hyperconjugation, as there is no bond between them, that is also known as your no bond resonance. So next is factor is your resonance stabilization. So resonance stabilization is your conjugation through, if you have a carbocation which is in conjugation with a pi bond. So now this carbocation can get delocalized to other atoms through resonance, or it can be spread out to multiple carbons. So you just see carbocation would be stabilized by your electron pushing groups, and whenever you can just spread out the charge through over multiple carbons, because whenever it is localized it is less stable, so when it gets delocalized it becomes more stable. So one factor is it should have a electron donating group which is attached to it, or it can get stabilized through resonance, or it can get delocalized. So in this case, as you just see, in this case you have a resonating structure. This positive charge can be spread out to this carbon. So now there is equal chance, there is chances of positive charge on this carbon and this carbon. It is no longer delocalized onto one carbon, rather it is delocalized onto all these three carbons. So the structure is a resonance hybrid of these two structures. Suppose we have a carbocation, that is your secondary carbocation. This is also secondary carbocation, but this is also secondary carbocation. But here we do not have resonance concept. So that means this is only being stabilized by plus I groups, and here we have resonance. So allylic carbocation is more stable as compared to your non-allylic or just simple your carbocations. And when you have aromatic rings, that also stabilize your positive charge through resonance. For example, your benzylic carbocation, okay, this is your benzylic carbocation that is being stabilized through resonance, because here benzene acts as a electron pump, or electron, it pushes electrons towards your positive charge, and now this positive charge is delocalized onto your benzene ring. So if we increase the number of benzene rings, then our number of delocalizing structures increases, or number of conjugating structures increases, and positive charge get chance to spread over more number of carbon atoms. So in that way, that becomes more stable. Actually, this becomes so stable that this can be isolated, and its NMR could have been taken. NMR spectra could have been taken. Some carbocations are actually unusually stable. You just check in this case. These are the three cyclic bonds. The one is your cycloheptatrionyl cation. This is your cyclopropenium ion, and this is your cyclopentadienyl cation. In all these three bonds, you have resonating structures. Here also you have resonating structures, but these are very stable, but this is not as stable as this cyclopropenium ion. If you just check, the number of resonating structures is less in this case as compared to number of resonating structures in case of your cyclopentadienyl cation. But in this case, Now this would be a positive charge, and sometimes this carbon will be a positive charge, and in this case you would have 4. But if you just check, in case of cycloheptatrinyl cation, you have 6 pi electrons, and here you have 2 pi electrons, and here you have 4 pi electrons. These two are aromatic because it have 4n plus 2. This obeys Hockel's rule, 4n plus 2 pi electrons. So this obey Hockel's rule, which says that for an aromatic compound it should be planar cyclic. All these three are planar and cyclic, but in this case you have 4n plus 2 pi electron, here 6 pi electron, here 2 pi electron, here n equal to 1, and here n equal to 0. But in this case you have 4 pi electron, which is not actually obeys your 4n plus 2 rule. So this is anti-aromatic and this is unstable. So aromaticity gives more stability to your carbocation intermediates. And whenever you have a lone pair adjacent to carbocations, those are also highly stabilizing. For example, if you have a OH group adjacent to this carbon, now this carbon has a positive charge, and this is a carbocation intermediate, and this oxygen is having two lone pair of electrons. Now this lone pair of electrons can be donated towards your carbon, so that no longer remains, the positive charge no longer remains on carbon, it goes to your oxygen. So that somehow stabilizes your carbocation intermediate. But for example, if you just check only cyclo a cyclohexane carbocation and this carbocation where you have a piran cyclo, and then that is more stable, and even this one is less stable. This is secondary, this one is also secondary, but here that is just near to the oxygen, where delocalization or the donation of electron, lone pair of electron from oxygen is possible. In this case here it is not possible, so this is less stable, this is more stable. Similarly, you can just see that there are many other examples where donation of electron from your heteroatom, mostly you should have a heteroatom with a lone pair of electron next to the carbocation, next to the carbon bearing the positive charge. That increases the stability. Actually there is two contradictory effects are coming here. This is due to resonance, okay, electron donation, and OH group is again a actually minus I group, that is they are electron withdrawing groups through inductive effect. They are electron withdrawing groups through inductive effect because these are highly electronegative element, but resonance wins here. Resonance is a stronger effect as compared to your inductive effect. Next, some destabilizing factors, like what destabilizes your carbocation intermediate. So for example, if we have an electron withdrawing group, it is already a positively charged species, so you have some groups who is going to withdraw electrons from it again, so then that would be more destabilizing. Just think that we are a poor country and again someone is there who is taking out loan from us, or who is taking out some monies from us, or we are having so many destabilizing conditions in our country, then that makes us more poorer and poorer. Okay, similarly, in this case, you just see this carbocation intermediate, we have a CH3 groups and other alkyl groups. Here we have just replaced hydrogen with three fluorines. So now this fluorine are more electronegative elements. So in turn, what they will do, they will attract electrons more towards itself. So now that gives this carbon a positively delta plus character. So that means this is an electron withdrawing group. So this is a very destabilizing condition. Already you are electron poor and someone is there who is taking out again electrons from you. Similarly, you just see in this case you have nitrogen bonded to carbon, so its lone pair of electron is delocalizing here, and it is stabilized by the lone pair of nitrogen. But when you have an ammonium ion, that means this nitrogen, you do not have any lone pair of electron, this is an ammonium ion, so that destabilizes your carbocation intermediate. uh, for example, when we have nitro group is a very strongly electron withdrawing group. SO2R group, those are very strongly electron withdrawing group. And if we generate a C plus here and we have a CO, again we have a delta plus here, this acyl group, so that is also a destabilizing condition. Presence of cyanide group, this is a very strong withdrawing group. So whenever we have a electron withdrawing group next to the carbon bearing the positive charge, that is a very, that destabilizes your carbocation intermediate. So for example, in this case, suppose you say that cyanide group, on the nitrogen we have a lone pair, but this nitrogen lone pair, it is not stabilizing. Okay, so that's why this is insignificant resonance term, it has an insignificant resonance term. Next comes your non-classical carbocation. Whenever you just see here, everywhere we have a carbocation where it is delocalized by your pi electrons, it is centered on a carbon, or delocalized your pi electron. So what about you? Those are known as your classical carbocation. Then there is non-classical carbocations, which are actually, there is not a pi bond in not conjugation, and it gets stabilized by neighboring group participation by pi or a sigma bond. So it is being stabilized by a neighboring group. For example, your cyclopropyl carbonyl cation, so this one, you do not have any pi bond here, just this bond delocalize onto this, so that gives, that is stabilized by your neighboring group. Similarly, it you have a phenonium ion, 7 norbonyl we will deal with this non-classical carbocations in our next reactions. So similarly here also, if you have a carbocation intermediate, so it is not conjugated to a pi bond, but still this pi bond is in perfect position to give electrons or to stabilize this carbocation. So now this forms a actually three centered two electron bond, three center two electron bond, which you might have come across in diborane structure. So here you have two electrons, and now this positive charge is delocalized onto these three carbons, and you have in total two electrons. So another concept is in this neighboring group participation, because non-classical carbocations are mostly stabilized by your neighboring group participation. So neighboring group participation is actually the effect of a group attached to a carbon atom adjacent to that carbon atom where nucleophilic substitution takes place, or the group leaves the carbon atom and leads to the formation of a carbocation. An increase in the rate of reaction by NGP, or that is your neighboring group participation, is known as your enantiomer assistance. For example, in this substitution reaction, nucleophilic substitution reaction, the group which is present just adjacent to that carbon, okay, that takes part. It works in such a way that it bonds with carbon, and it actually facilitates the departure of this leaving group, and then nucleophile attacks, and it uh, gives you the product. And by the presence of this group, actually this increases the rate of reaction. So this is actually if you just see the product, there is, you cannot see that this group has taken part, but just it is a nucleophilic substitution reaction, but the rate of reaction is increased by the presence of this group. So that means it is playing some part in this reaction. So this is known as your neighboring group participation, because just present in your neighbor of this carbon. And as it increases the rate of reaction, this is known as your enantiomeric assistance. So for example, this is your starting material A, and it goes, first it gives you one transition state, then it gives you a normal carbocation intermediate which undergoes rearrangement to give you another non-classical carbocation intermediate, and that gives rise to your product. So in case of your non-classical carbocation intermediate, so you get two different transition states. So for example, if you have a aromatic ring, as there are many type of neighboring groups. For example, in this case, aromatic ring acts as a neighboring group. So in this substitution reaction, tosylate is first being substituted by the neighboring group, which is your phenyl group is present. That first uh, takes part in your, that pushes out, we can just say, that attacks here, and it forms a intermediate cyclic phenonium ion intermediate. And again, now this OAC, that is your acetate, the nucleophile can attack both the sides. Okay, so it depends, like 3 orders, it should be it. Okay. Next, carbon-carbon double bond acts as a neighboring group also. So uh, in this case, whenever the leaving group departs to give you a carbocation intermediate, now this carbocation intermediate will be stabilized by your this group to give you a non-classical carbocation intermediate. This is simple classical carbocation intermediate, and that becomes your non-classical carbocation intermediate. Then the nucleophile will attack to give you the product. Similarly, carbon-carbon single bond can also act as a neighboring group in the rate enhancement of your reactions. For example, in this reaction, brosylate, first it leaves to form a carbocation, where generate a carbocation, and then this group migrate to give you a carbocation intermediate, where the actually positive charge is delocalized onto 3 carbon centers. Then again it can attack at carbon number 1 or carbon number 6, attack at carbon number 1 or carbon number 2, giving rise to your, that is going to give you the same product, whether it is attacking at 2 or 6. Similarly, methyl can act as a neighboring group also in this neopentyl tosylate. So first this CH3 group attack here, and tosylate leaves, and again whenever, so now you can have to, whether the nucleophile can attack this carbon or it can attack this carbon. So depending on which side it is attacking, this carbon-carbon bond will break. So in case of your, how you know that you have a neighboring group participation? Suppose we have a normal SN2 reaction. For in this case, we have started with S enantiomer, we would get your R enantiomer. Simple SN2 reaction, the nucleophile will attack from the backside of this carbon and you get your product. But if this reaction, actually here it is taken place in presence of sodium hydroxide, so that is a normal SN2 reaction. If this reaction is carried out in silver oxide, then it was seen that you get a, whatever the enantiomer, suppose you have taken S here, you are getting S. That means it is not SN1, because in case of SN1 you get racemic, not SN2, because in case of SN2 you get the inversion. If you take S, that is going to give you R. So this is twice actually inversion, 2 times SN2. So first your OH group attack here, inversion in config, first inversion, then again another OH minus is attacking. So here 2 SN2 reactions are taking place. So that means as you are getting SN, means retention in configuration, you have taken S and you are getting S. So that means you have 2 SN2, 2 inversions. So that suggests that there would be first one internal nucleophile, then your external nucleophile is coming. First internal nucleophile attacks, the leaving group departs, and then your external nucleophile attacks. So that takes 2 inversion to give you overall retention. So if you see a substitution reaction at a stereogenic center that goes with retention of chemistry, retention of stereochemistry, look for neighboring group participation. Next are some rearrangement reactions of your carbocations. So general rearrangement reactions are, for example, suppose we have a nucleophilic substitution reaction. So it would be reaction, we generate a carbocation, nucleophile will attack here. That gives you a simple reaction. So that gives you the product. Here there is no rearrangement. But sometimes what happens, for example, this reaction, you just see. I just lost it somewhere. Okay. So instead of, suppose we have, I lost that one. Okay, no problem. Suppose I have CS3, CS3H, H2, Cl. Okay. Uh, I would have a CS3 here, I think. Okay, so the end product of this one should be the chlorine would go out from here and it would give me OH only. But the end product is not that one, so that gives CS3, CH2. The OH would be here, and here we have a CS3. So that gives actually a that gives a rearrangement product. For example, in this case, mm, you just see we have a primary carbocation here from whatever be the generation. So now this primary carbocation, here we can have a 1,2 hydride shift or a 1,2 alkyl shift. If 1,2 hydride will be shifted, then we generate a carbocation which is a tertiary carbocation. If 1,2 alkyl is shifted, we get a carbocation which is a secondary carbocation. So this one is a tertiary is more stable as your secondary. So this shows like the rearrangement where you have one group is migrated to generate another more stable carbocation intermediate. In case of your addition reactions also, these carbocations can undergo addition reactions. Even alkylation reaction, that is in case of a Friedel-Crafts alkylation reaction, that also involves your carbocations. And this is the mechanism of your alkylation reaction, where you first generate your al- carbocation electrophile, then it is a substitution, electrophilic substitution reaction of your aromatic compound. Similarly, in case of your acylation reaction, you generate your acylium ion, and then it undergoes your acylation electrophilic aromatic electrophilic substitution reaction. Even your carbocation intermediates, carbocations can take part in your chain polymerization reaction. So now this carbocation will again be attacked by another carbon-carbon double bond, so the reaction goes on to form a polymer. So some important rearrangement reactions of your carbocation. So first one is your Wagner-Meri rearrangement. So this is a class of carbocation 1,2 rearrangement reaction in which a hydrogen, alkyl or aryl group migrates from one carbon to a neighboring carbon. They can be described as cationic 1,2 sigmatropic rearrangement proceeding superficially with stereochemical retention. We know that in case of your rearrangement reactions, we mostly get your stereochemical retention reaction. So this is mostly nucleophilic substitution reaction. For example, this one, you just see, and this is a primary carbon where your bromine group is attached. So it does not undergo general SN2 reaction or SN1 reaction. Rather, the product formed is a rearranged product. So what happens here? First, bromine group is left to generate a carbocation intermediate, which is a primary carbocation, and it again undergo 1,2 methyl shift to generate a more tertiary carbocation intermediate, and finally water will be added to give you this alcohol. Actually, if we just could have add OH here, this should be formed neopentyl alcohol, which is never found. Even the same with neopentyl alcohol, that generates your tertiary amyl chloride. For example, in this hydrochloric, in this addition reaction, we think that okay, that will undergo addition to give you the normal Markovnikov addition product, but that does not take place. First, it would take out proton to generate a CH plus here. Okay, CH plus here. Then in this carbocation intermediate is less stable, that is a secondary carbocation. So this undergo a migration of your CH3 group to that one to form a tertiary carbocation. Now it can undergo elimination reaction from, actually it has to take beta hydride elimination, it will take hydrogen from this carbon or it can take hydrogen from this carbon, but this one is more stable because this is the most this is your Seth-Gibbs rule. The more substituted alkene will be favored. Okay, for in this case, isobornol that gives you camphin. So whenever you have this kind of compounds, it is better you whenever you are checking rearrangement reaction, you always number the carbon atoms. So then it would be easier for you to trace the pathway to predict the product. For example, in this case, we have just given number 1, 2, 3, 4, 5, 6, 7. Okay, 6 contains your OH group. So in presence of H plus, that gets protonated OH group gets protonated, and then you have the departure of your water to generate your carbocation intermediate. Now this carbocation intermediate is stabilized by the sigma bond, 4,5 sigma bond. So now your 4,5 sigma bond is migrating to 6. That means you are forming a bond between 4 and 6, and 4 and 5 bond is broken. So in that way, 5 you have a carbocation, you have a positive charge on carbon number 5. So you can just look it or rotate it the structure in such a way that it will look like this. So now this positive charge, you have a hydrogen here, so now that undergoes elimination to give you this product. So this intermediates, actually in rearrangement reaction, what is the main factor is that the carbocation intermediate just gets stabilized, so it increases the stability of your carbocation intermediate. Not only the stability, but also if you have a angle strain, torsional strain, or steric crowding in the reactant structure, this can be also relieved by such rearrangement reactions. For example, we have a 4-membered ring here. So in this case, we have a OH, like this OH group first gets protonated to give you OH2 plus, then it would be removed to generate a carbocation intermediate. So now we have two chances: either the this bond will migrate here or the hydrogen will migrate here. In both the ways, we are going to get a tertiary carbocation, but still, if this one is being actually, we can have hydride shift that will generate a secondary tertiary carbocation. But if we are removing this one, if we are migrating this one or shifting this bond, then that is generating a secondary carbocation. But this one is being formed, the reason is it has relieved the torsional strain, the angle strain, because this is a 4-membered ring, it is a 5-membered ring. 4-membered rings are less stable as compared to your 5-membered ring. Okay, so this is being formed, and then you get the final product. So this is a very nice example where carbocation intermediates reduces the angle strain. So this we have 4 3-membered rings actually, and by this rearrangement reaction, they are relieved to 3-membered rings are relieved to form your 4-membered rings. How it is being formed? So first it is giving you OH2 plus, that it would generate a carbocation intermediate now. So now that would go to this one, this bond will break, this bond will migrate to this one, that will generate a 4-membered ring, and again it will generate a positive center here. So this one will again migrate towards this will generate a positive. So this goes on, this cyclically goes on until all the rings are 4-membered rings. And there is another rearrangement of your ring expansion, in which mostly in case of your that is your Tiffano-Tenzanov rearrangement, it is actually the treatment of your alpha hydroxyamines with your nitric acid that first forms a diazonium salt, then again it undergoes a series of reactions where bond breaking and migration of groups takes place to finally give you the ketone. So this undergoes, actually mostly does in case of your cyclic compounds. For example, here we have a ketone, cyclopentanone. We can just treat it with hydrogen cyanide to form a uh, cyanohydrin, and this cyanohydrin can be can be reduced to form a primary amine. So now this primary amine can undergo diazotization to form a diazonium salt, and it can undergo your diphenodimjanov rearrangement to give you the main product. So starting from your cyclopentanone, you can get cyclohexanone. Similarly, from your 1 aminomethyl cyclohexanol, you can get from cyclohexanol also you can get your cycloheptanone. So these are this is the rearrangement for your ring expansion. Mostly they have used it for your ring expansion. Next comes your pinacolone rearrangement, in which actually uh, pinacolone rearrangement. So this pinacol is derived from your ketones. So this pinacol, when treated with sulfuric acid, concentrated sulfuric acid, it undergo rearrangement to give you a pinacolone. So as you can just see, in case of pinacol, two CH3 groups are, this is a symmetrical alcohol actually, two CH3 groups are on this carbon and two CH3 groups are on this carbon, but in the end product there is three CH3 groups on one carbon. So this has rearranged. So this rearrangement is your pinacolone rearrangement. This takes place in the presence of an concentrated sulfuric acid. So when sulfuric acid is added, one of the OH, the mechanism is the one of the OH group gets protonated and it departs to generate a carbocation intermediate. So now this carbocation intermediate actually what happens, we have a OH group next to it. Okay, this lone pair of electron now stabilizes the positive charge which is going to be formed here, and this methyl group gets migrated to this carbonyl carbon, and then this loses a proton to give you a stable ketone, that is the product. So for example, in this cyclic compound we have two OH groups. This is nothing but we have just same as your pinacol, we have two OH groups. Now one of the OH group is protonated to generate your carbocation. So when that lone pair of oxygen becomes involved, like we do not have a group here, rather we have a bond here, so this migrates to your carbocation. So now it uh, increases the carbon number in one ring, that is 6 membered attached to your 5 membered ring. So this is a very good reaction to form your spiro compounds. Spiro compounds are actually two rings joined together by a single carbon atom. Similarly, in this case, okay, so up to now, whenever we are dealing with your symmetrical carbons, symmetrical alcohols. So which group is migrating, it does not matter, and which OH group is getting protonated, it does not matter. So now in this thing, we have two different type of groups attached to it, and we have two different OH groups here. So in these two different OH groups, first we will check which OH group is going to be protonated. So if this OH group is going to be protonated, that is going to generate this carbocation intermediate. Okay, and if this green OH group is getting protonated, then we are going to intermediate and this carbocation intermediate. If we just check this carbocation intermediate and this carbocation intermediate, among this is a secondary carbocation, this is also secondary, but we have two no, this is a tertiary carbocation, and again, okay, this is also tertiary, this is also tertiary, but here we have two phenyl groups or two benzene rings which is attached to a positive carbocation, to a carbocation intermediate. So this is more stable, so this will be formed, and now there is this OH group will push its electron, and this bond will be migrated to this carbon 6 to form a bond with 6. So this product is formed, this product is not formed. Okay, so this is about the first of all, the first step is the formation of a carbocation intermediate. So first you have to check which carbocation intermediate is going to be formed. The one if we have two possibilities, the one which is more stable, that would be formed faster. So the next step of the reaction depends on that carbocation intermediate. So next is, suppose we have same type of carbocation intermediate, like, okay, as per example, in this case it would generate the whether this OH group is protonated or this OH group is protonated, that does not matter, because they are going to give you the same carbocation intermediate. Whichever OH group is protonated, that is going to give you the same carbocation intermediate. So next step is our migration of the group. So whenever we have a migration of a group, here we have C6H5, that is a phenyl group, and a methyl group. So which one is going to be migrated? If methyl group is going to be migrated, if methyl group is going to be migrated, then this would be the product, and if phenyl is going to be migrated, this would be the product. Then it depends on the migratory aptitude of the groups. In this is the migratory aptitude of the groups. So in this case, C6H5 is have more migratory aptitude as compared to your CS3 group. So that's why C6H5 would be migrated to give rise to this product, not CS3 group. So you will have many different examples of pinnacle rearrangement. This is a semi-pinnacle type of rearrangement. As you see, if we not only here we have used diols, 1,2 diols. Instead of 1,2 diols, we can have other groups also, like amine and alcohol. So when we treat nitrous acid with this compound, so that first generates a N2 plus. That is the generation of, actually this one is being used to generate N2 plus, which is a good leaving group. The same purpose of using your sulfuric acid, that makes one of the OH groups OH2 plus, which would be a better leaving group. So that generates this N2 plus. Now among this we have the same C6H5 group, one would be migrated, so that would be the final product. Same is here. So here in this reaction, you just see when we have N2 plus, OH group will migrate, so this group would go there. So we have a decrease the size of your ring. So there is another kind of, that is your semi-pinnacle rearrangement, in which you have, if you just see here, we have same type of OH groups. All the two are your tertiary alcohols. Here we have a tertiary alcohol and we have a primary alcohol. So first what they do is selectively using tosyl chloride, that selectively tosylates your OH group, that is the primary alcohol. Then it can undergo same kind of your pinnacle rearrangement, that would leave, that generates a carbocation intermediate here, and this OH lone pair of electron pushes, and this ring gets expanded to give you this product. Next rearrangement is your benzylic acid rearrangement, from benzyl to benzylic acid. This is a kind of nucleophilic addition reaction with an your rearrangement. So first of all, your we have an OH minus, so that will attack this, attack the actually attack the carbonyl carbon, and now from the tetrahedral intermediate that forms this tetrahedral intermediate. So this tetrahedral intermediate rearranges in such a way that the pH group migrates to the other carbonyl carbon, and then that gets protonated to give you the product. With alkoxide, suppose you do not have a, OH group, if you have alkoxides, so that leads directly to esters by the same sort of your mechanism. Next intermediate is your carbanions, where carbon bearing a negatively charged species. So how we generate your carbanions? There are different reactions where you generate carbanions. For example, your decarboxylation, in which you generate carbon dioxide is removed from a carboxylate ion and generating one carbanion. Even if we abstract one hydrogen by a base, then also we can generate a carbanion. For example, in this hydrogen, okay, in this molecule, these two hydrogens are acidic because that is present near to a carbonyl group. So that abstraction of this hydrogen or that proton generates a carbanion. Or even if we add a nucleophile to one unsaturated compound, that also generates a carbanion. Or if we attach a metal, that is your electropositive metal, to your react with your alkyl halide, then that also generates a carbanion. So what are the structure of carbanions? If you just see, carbon is having a negatively charged species. So now we have 5 electrons and you have 3 electrons taken part in bonding. So in total, it is 3 bond pair plus 1 lone pair. So it is 4 electron pair. That means it has to be sp3 hybridized, having a lone pair of electron. So this lone pair of electron is present in an sp3 hybrid orbital. So this assumes a pyramidal shape, so which can actually, if all the three groups are all these three groups are different, then that should be chiral, but they are not resolvable because that undergo inversion, rapid inversion, from one pyramidal form to the other. So you cannot resolute your carbanions. Okay, what are the stability of carbanions? So you just see carbanions are negatively charged spaces. So whoever is taking out electron from it, then that would be more stable. So first of all, it depends on the S character of the carbanion carbon. So the more the S character, the more stable it is. Because if you just see, this is your ethyl carbanion, this is ethylene carbanion, this is your acetylene carbanion. The reason is it is a negatively charged species, so that will like to stay closer to the nucleus. So here our S character is more, that is here 50% S character, here we have almost 33% S character, and here we have 25% S character. So this is 50% S character, means S is your spherically symmetrical, more S character, that is sp hybridized orbital. So this is more close to nucleus as compared to sp2, as compared to your sp3. So as it is more close to nucleus, so that was more stable. So these are the pKa values for some carbon acids. So from that you can just say which carbanion is more stable. Okay. Next is inductive effect. These are stabilized by inductive effect. That means presence of minus I groups. It would be just opposite of your carbocation stability. So I won't go with detail. So the presence of a minus I group increases its stability. That means we can just say presence of electron withdrawing group stabilizes it, whether it is a through resonance or whether it is through inductive effect, because this is a negatively charged species. So whenever someone is taking out electron from it, it stabilizes that. So in that way we can just say that this CH3 minus is less stable as compared to CH2F minus, less as compared to CH F2 CF3 minus. So this is very stable, CF3 minus. Okay, and methyl carbanion is more stable as compared to primary, as compared to secondary, as compared to tertiary, because in this case you have a plus I group. In this, in case of secondary, you have two plus I groups, and in case of tertiary, you have three plus I groups. So this would be destabilized. But in this case, you have your minus I groups, and destabilizes whenever through resonance also you can just check the stability. So for example, you have this acetonitrile, the presence of you can just, when you take out this base, take out this proton, that generates this carbanion, which can be stabilized by your resonance. So similarly, benzyl carbanion is also stabilized by resonance. From this, you can just infer that this benzene acts as a electron sponge actually. Whenever one carbocation intermediate is there, CH2 plus, then it gives electron, and whenever you have a CH2 minus, it takes out electron. So this benzene ring acts as an electron sponge. So the effect of various groups on the stability of carbanion is if nitro group is present, that stabilizes more as compared to acyl group, as compared to your ester group, sulfur dioxide, cyanide. So these are the orders. So cyclopentadiene. So you just check in the previous carbocation intermediate, we have checked that cyclopentadienyl carbocation is less stable as compared to your cyclopropenyl carbocation. In that case, you have 4 pi electrons, although this is actually conjugated, but still this is less stable because it has 4 pi electron. But in case of your cyclopentadienyl anion, you have 6 pi electrons, and it is very stable because this is aromatic. So aromaticity also plays a role in the stabilization of your this carbocation and carbanion ions. So these are also very stable because you have an electron withdrawing group here, you have an electron withdrawing group here, you have an electron withdrawing group here. They are very stable. Next is some general reactions of carbanions. So carbanions can react with any general Lewis acid to undergo this type of substitution reaction. So this can act as a nucleophile, this can react here, and this will leave. This can act as a general displacement reaction. For example, in this case, this can also, we use it in case of your addition reactions also. First generation of your carbanions, then it can add to this one by displacing your bromide ions. This can also involve elimination reaction, in which first would be the generation of your carbanions and then elimination to give you your alkanes. So for that, for this type of elimination reaction, there should be an beta hydrogen present there. And it can undergo Claisen condensation reaction, in which two molecules like it condense to your carbonyl carbon to generate your product. So there are many different type of reactions you can just see in case of your carbanions. This is the condensation reaction, aldol, very famous aldol condensation reaction, in which we should have a uh, alpha hydrogen uh, present in your carbonyl compound. So this alpha hydrogen first, it gets deprotonated to get this carbanion, and then this reacts with the carbonyl carbon, undergoes addition, and then it one H2O would be removed to give you your condensation product. So this is a Dickman condensation reaction. So they can undergo many condensation. Next comes your addition reactions, in which one is your Michael reaction or Michael addition. This active methylene compound, this is your active methylene compound, because this hydrogen, this is being formed by the removal of the hydrogen that form a uh, carbanion ion, and this is more stable. That's why this compound are known as your active methylene compounds, because this methylene is very active. It can, yeah, if you remove, you can remove this hydrogen because this one is acidic. Okay, so this carbanion undergoes Michael addition reaction. Michael addition reaction is your nucleophilic addition to one alpha beta unsaturated uh, carbonyl compound at the position number 4, that is the conjugate addition, that is your kinetic product. If you remember, we have discussed about the kinetic product. So then some rearrangement reactions of your uh, carbanion. One is your Fibers-Key rearrangement, in which your alpha haloketones in presence of an sodium ethoxide or sodium alkoxide, that gives you a carboxylic acid derivative. So this reaction involves, first it undergoes the departure of living group, then, okay, no, so first what happens, I don't think I have. First attack of your nucleophile on this carbonyl carbon, and then it comes back and this goes react here and this leaves. So that gives the carboxylic acid derivative. So if this reaction is carried out in cyclic ketones, it results in ring contraction due to rearrangement. For example, in this reaction, suppose you have this reaction in presence of an acid that takes out this proton, that generates this carbanion, it go there, then that gives the series of reaction to give your carboxylic derivative. You can take all these reactions. Next is your 2,3 Wittig rearrangement. So this allows the synthesis of your homoalkyl allylic alcohols by the base-induced rearrangement of our allyl ether. So this is known as your 2,3 Wittig, because this is 1, 2, 3, and this is your 1, 2. So on this side 2, on this side your 3. So you have to write it in this way. So first of all, this proton will be because this is your acidic proton, in presence of your base, that proton will be eliminated, and this undergoes a cyclic reaction, that is in a concerted manner. This bond reacts here, this comes here, and this goes there. So that gives you a homoallylic alcohol. Similarly, you have a Stevens rearrangement, where your quaternary ammonium salts and sulfonium salts can be actually undergo rearrangement to give the corresponding amines and sulfides in a 1-2 rearrangement. 1-2 means first 1 and 2. Okay, so this first your generation of your uh, carbanion by taking out the proton from here. This proton is more basic. You can just see you have a acyl group here on this side, and you have a N plus on this side. So this carbanion, which is formed by the proton abstraction, is more stable. So this proton will abstract to give you this carbanion. Now this carbanion can go like this to generate this carbanion. Again, this one will be, this bond will be broken, not other bonds, because this one will generate the more stable carbanion. Again, this stable carbanion will react, attack here to generate your amines, tertiary amine. Similarly, you can reduce the mechanism of this reaction. Next is your last one, ambident ions and their reactions. Ambident nucleophiles would be defined as the nucleophile species that have more than one atom per attack to result in different structural isomers. So ambident nucleophile means you have two different nucleophilic centers, I will say. For example, in case of cyanide, you have uh, you have a carbon on negative charges on carbon, so that is a nucleophilic center, as well as on nitrogen you have a lone pair of electron, that is also an nucleophilic center. So these are known as your ambident nucleophiles. So depending on the reaction conditions, they can attack on any side. So this is your thiocyanate, it would be your isothiocyanates. So similarly, in case of your this active methylene compounds, you can have a negative charge on carbon or negative charge on your oxygen. So these are the resonating structures. So now this can, whenever we do alkylation, we can alkylate, we can do O alkylation or we can do C alkylation. So depending on your reaction conditions. Okay, for example, we can just check the reaction of your ambident nucleophiles for phenoxide ions. As we know that phenoxides can undergo delocalization to give you, it can have negative charge on oxygen, or it can have negative charge on ortho and para carbons. So here we have two, or one ortho and one para carbon is there. So it can either undergo O alkylation or it can undergo C alkylation. But if you just see in this particular example, in 2,6-dimethyl phenoxide ion, you would get major product would be your C alkylation, because due to the presence of methyl groups at ortho positions, O alkylation is difficult. Similarly, this also depends on your solvents. For example, here we can have N alkylation or C alkylation. By the virtue of delocalization, you can have negative charge onto or your position number 2. Okay, so you can have so it can undergo N alkylation on N, or it can undergo C alkylation. So depending on your solvent conditions, as you decrease the solvent polarity, C alkylation increases, because if you decrease the solvent polarity, there would be less negative charge on your, or this compound would be less polar. So in that case, C alkylation would be the main result. Next is one is your NEF reaction, in which you have a nitro group, which is also an ambident nucleophile, in which you can have negative charge on carbon and you have a negative charge on oxygen. So when you treat it with H2O2, that is your hydrogen peroxide, that is a soft nucleophile, so that would attack actually at the soft end, that is at the carbon, and giving you this product. But if you use this reagent, which is a very strong alkylating reagent, that will primarily go to your hard part, that would alkylate your oxygen. Similarly, in case of your active methylene groups, you can have O alkylation or C alkylation. So that depends on the softness of your leaving groups. So if you have bromine, chlorine or fluorine are used, that in that case your C alkylation would be more. But when you have X tosylate and all those things, hard groups, then you have O alkylation as the major product. Next is your cold nitrile synthesis, in which actually in presence of, this is a nucleophilic substitution reaction. If you use KCN, then you are getting cyanide. But in presence of KCN, if you use AgCN, then that is going to give you isocyanide, RNC. The reason is, in case of your potassium cyanide, this is ionic compound that generates K plus Cn minus, where the negative charge is on carbon. The nucleophilic center is carbon. But in case of silver cyanide or copper cyanide, these are not that ionic. These are covalent bonds. They have more covalent character. So that in that case, it is not ionized completely to Ag plus or cyanide minus. So in that case, first the lone pair of nitrogen acts as your nucleophile, so that bonds to your this carbon, forming your isocyanate. And so, okay, same thing I have just repeated here. Okay. uh, Next is your reaction with phenoxide ion. For example, if we do the alkylation of phenoxide with this trinitrobenzene, so in that case, this we know that this position is going to be your thing, but just the thing is that it whether it is getting O alkylated or C alkylated. So it can either get O alkylated or C alkylated depending on your reaction temperature, because one is your thermodynamically stable product and one is your kinetic stable product. So the first one, attack through oxygen end, is found to be reversible and kinetically preferred, as the formation of the adduct does not disturb the aromaticity. Okay, so it can just react with the O alkylation. Here we have O alkylation, so this is your kinetic control. The aromaticity of this ring is not disturbed, so kinetic control. But C alkylation, it at C it gets alkylated. That is your thermodynamic product, which is your most stable product. So that finishes today's part. So and if anyone is having any doubt, you can just ask. Any doubts? No one is having any doubt?
No, ma'am.
Okay, no problem. Then you can just go through the. Uh, I have sent last 2 days presentation slides. So I think your friends might have shared with you.
Yes, ma'am. We have
Yes,
got
ma'am.
it.
I have said.
Okay, okay. So I will also send today's presentation. Then if you have any doubt, we can ask tomorrow also. Just go through it and you just check your IGNOU site where you have your questions. All the questions are there. MCH 011, 012, all the questions are there. Previous year questions.
Okay.
Okay.
Thank you, ma'am.
Yep.
Thank you, ma'am.
Okay. Good night.
Good night, ma'am.
Good night.